Hey folks, sorry for the delay. I guess I was just waiting for someone to walk in and let us know that we could start, but let's get started. It's really good to be here and talk about something that's been cooking for a while. We're really excited to sort of unveil it at this point. But first, my name's Manmeet Singh, and I work as a developer relations engineer with the Starknet Foundation. I'm here with Milton from Wake Up Labs. And today we're going to tell you how you can implement privacy-preserving dApps on Starknet using Noir. I also just want to say that we're really excited about this collaboration because it does unlock a whole new space for innovation where you can use the kind of hybrid ZK model that Aztec has innovatively sort of created and plug that into the hyper-fast, scalable solution that we have over at Starknet with Stark proofs. So just by a show of hands, how many people here have actually used Starknet or ever tried to program in Cairo? You should have a good reason, but okay, so a few people, I see. So let's just start with a quick refresher on Starknet. If you've been following rollups on Ethereum, you probably know that Starknet is a validity proof-based L2 on Ethereum that uses scalable and transparent arguments of knowledge, ergo Stark proofs, to process transactions in a way that is fast and cheap and also theoretically post-quantum secure. But what does that actually mean? Actually, I don't think we need to because we're running a little late and short on time. But Starks are basically a transparent construction of zero-knowledge proofs that are battle-tested. They've been in production since for at least 3 or 4 years at this point. You don't need to have a trusted setup or any securely generated parameters for a proof object. They use the randomized Oracle model and hash-based commitments. And Starknet has actually proven to be fairly performant. It had up to 600 plus user operations per second last week, and it was able to process subset ERC20 transfers as well. And of course, all of this it's just this one. All of this is, could you go back a slide, please? Thank you. All of this is based on our programming framework for Stark proofs, which is Cairo, which you can kind of think of as being an analog to Noir, but for Stark proofs. It's a Turing-complete Rust-like programming language, which is based on a research paper by the same name, Cairo CPU for Arithmetic Intermediate Representations. And I want to also point out that Cairo is not exclusive to Starknet. As I mentioned, it's a Turing-complete programming language, and the prover engines that are used to generate these proofs, namely Stone or Stark1 and Stu, which is the second iteration of it, are open source. You can find them on GitHub, and you can use them, sort of akin to Winterfell, which is, I guess, a better known repository there. You can go to the next one. I guess this is a bit redundant. Everyone here knows what Noir is. But the thing to point out is that Noir uses snark proofs. I guess that makes sense for privacy-preserving transactions just from a performance point of view. But again, Noir is Rust-like. Again, interesting little distinction there. Cairo and Noir, syntactically Rust-like, but quite dissimilar under the hood. But Noir does provide an efficient and developer-friendly environment to generate circuits for snark proofs. It's called honk, right? Like optimized blunks. Right. So you can go over to the next slide. So can anyone guess what the problem is? Like, why can you take, like, generally you could take a snark proof, but like, what's the main difference between a Stark and a snark proof that makes them difficult to interoperate between each other? Anyone want to take a guess? You want to say something?
The second letter.
It is the second letter, basically the second letter. Basically, so you've all probably used Bitcoin at some point, and ever since Bitcoin, it's been common practice in most blockchains to use elliptical curve-based cryptography, elliptical curve-based signatures, ECDSA, and so forth, so on and so forth. Now, most ZK schemes actually use commitments, right? Like commitments form the bedrock of a lot of ZK schemes, and traditionally, like the Snark and the slightly older, I can't even believe I'm saying older, it's also new relatively, but like Snarks use elliptical curve-based commitments, whereas Starks use hash function-based commitments, which is based on a trust model called the random oracle model. And you can read up on that more, and I can also talk about that later once we have more time. But essentially, you cannot verify a Snark proof in the same way that you verify a Stark proof. So what you need over here is some method to basically implement the kinds of elliptical curve libraries at a high level in Cairo so that you can verify Snarks in Cairo, then prove that Cairo program using a Stark proof and verify that as a Stark proof. So it's kind of like wrapping a Snark into a Stark. So how do we do that? And there are some challenges here. So traditionally, like these little software tools that you need to verify. What you really need is a way to multiply across elliptical curve points. Like you can add elliptical curve points across traditional commitment schemes. You can multiply them, so you need something called elliptical curve pairings. And it's kind of tricky to implement. So what we did is, or what people in the Starknet ecosystem did, is they implemented an open source library for elliptical curve pairings and provided those as built-ins, which you can kind of think of as being similar to, what are they called, pre-compiles in the EVM space on Starknet mainnet. So you can actually import these pre-compiles or built-ins into your smart contracts which on Starknet. The other really cool thing here is that every Snark proof requires a unique set of random parameters, meaning that pretty much every time you deploy a smart contract using Noir, you're going to need to deploy a customized verifier for that smart contract. Of course, they all follow the same sort of underlying template, but what this tool that people have built in the Starknet ecosystem called Garaga does is it also generates a new verifier each time you have a Noir smart contract. And that verifier is written in Cairo, and you can just deploy that on mainnet. And that allows you to have sort of this boilerplate code to verify your contract on Starknet using the relevant elliptical curve pairings. You can also then modify that smart contract that you have, the verifier contract, and add additional business logic. For example, if this proof is valid, then do this or that on like a fully on-chain game or a DeFi smart contract. If you want to learn more about Garaga and how it works, as I mentioned, it's open source. It's got some documentation. You can find it at that QR code. And that's kind of like the high-level theoretical overview of what we are doing. I guess we should see it in action now. And that's what the folks at Waco Labs have been working on. So I'll hand it over to you. You might also need this.
Okay. I put it here. It's okay. Thank you. Well, hello everyone. Super happy to be here. I am Milton Berman, co-founder at Wake Up Labs. We are a software development studio. We focus on building like at the edge of technology products. We always build blockchain and crypto. We do products and the apps for the crypto ecosystem. We have been working for a while, and we have been doing it with top players in the industry. That's why they trust us to build a complex solution, things that didn't exist before. And that's why what we like most, sorry for my English, that's not my primary language. What we like most is doing that, like kind of building the plane while you are in the air. That's where we have fun and where we think we add value to this industry. So yes, that's why Starkware and Starknet asked us to do this product for this demo. It's a POC in which we will showcase what Mamit was talking about, the possibility to use Noir language to generate proofs and validate them in Starknet using Garaga. So we built And just to wrap up about Wake Up Labs, if you need help on doing complex stuff, we are here to help you. If you have ideas, we can help you with that. Also, if you're an engineer or you are friends of engineers that love working on this kind of projects, we are hiring. So now going to the demo, what the Starkware asked us and proposed was kind of designing a token, a private ERC20 token. It's a token that will be with the same interface as the ERC20 that we all know. But in this case, everything that will happen on-chain will be private. Nowadays, all of you know that if we send transactions on-chain, you can see almost everything. It's pseudonymous, but you see the money where it goes. In this case, the idea was to generate this token in a way that all this information remains private in every user or every wallet. And as I said, we did it. We built a React native, a React JS app that uses Noir and also interacts with the Garaga. We built a smart contract in Cairo. So I will move forward with this. The project is named Enigma. You can try it there. It's on Sepolia testnet. It's a POC. It's intended for workshop and for demo purposes right now, but we can try it a bit. You can try it. Nowadays, you can create, you can mint tokens, and then you can send and receive, and also do some other stuff like in ERC20, approve or transfer from, all in a private fashion. If you have tokens there, or you can mint it in the faucet, you can try it. It is not typical that we show a live demo in person, in real life, but I will try it. I have a nice video of how this works, but let's do it now live, if you agree with me. I will go to a demo and then I will explain how it works. Enigma here. I will share here. There we are in Enigma. So I am here in the app. I can see my nodes. Then I will explain a bit about these nodes. It's the same concept as UTXOs in Bitcoin, you know. So all your balance is the summary, is the sum of all the valid nodes. You exclude the burned nodes, the nodes that you have used, they are nullified. That's your balance. Now I will send, I will open the other window here. Where we are. I cannot see. What? Let's try. I'm trying to show the. What? You believe me? There is another user here. Why? It is not working.
You can do view tab on this one. That's what it was.
This is full screen, maybe. Ah, there it is. So we have two different users here, one with the Arc browser, the other with the Chrome browser. They have balance. So I want to send some balance to this one. So then I will explain a bit of this, but each user has an address and also a public key for encryption purposes. I will try to send 0.04 to this guy. So here we connected with the Argent wallet. If everything works as expected, we will do a transaction there. The thing that will happen is that we will be generating proofs locally in the browser. Where we state that we have this money and we will send it to this guy, and it will remain on chain, but nobody can understand what is happening beside these two guys. So there is a transaction here in Starknet. It has these proofs. Yeah.
So this is a Zcash-like protocol with nullifiers that one can...
It's yes, it's inspiring Zcash, exactly. Yeah, using ERC20 interface and working. Yeah, exactly. So this transaction happens on Starknet. The proofs that we generated in our local machine using Noir, they come to the smart contract in Cairo with the help of Garaga. And here we receive this node. And if you go to the transaction, you will never understand what happened here. We can do a lot other stuff. I won't show it. You can try it yourselves. Kind of approval or transfer froms. I will continue here, and I will show a bit of how this works. So as we saw just before, we have a receiver that shares his address and public key to the sender. The sender, when you load the app, you have to know your balance, and the way to do it is to fetch every commitment that there is in blockchain. I will explain what is a commitment, but it's just when you send, you kind of, it's the UTXO way, kind of you create a node and you sign it and you encrypt it and you send it to the smart contract, and that is on chain, and there is a Merkle proof with every commitment from everyone that is transferring tokens. So to know your balance, you have to go and look for every commitment in the smart contract and check if you can decrypt it or not. If you can decrypt it, you are the owner of that node, of that commitment. If you cannot, you pass along to the other. So then you have a full balance. When you have the balance, you select which node you will send or which commitment. You generate the CK proofs as we have just seen. You generate locally, and then you send it to a blockchain. In this case, we go directly to a blockchain, but we could have a relayer in the middle. You have more privacy if you add that. And you send the transfer. And what happens when, let's say I send a node with, I don't know, 1 Enigma token, and I want to just send 0.8. So as the same in Bitcoin, kind of you nullify the 1 Enigma token node, and you do that on chain. So you inform to the blockchain that this node of 1 Enigma token is not useful anymore, and you generate 2 new nodes, one with 0.8 that you send to the receiver, and one with 0.2 that is a change for you. And after that happens, the creation of the new nodes, the nullification, the receiver can check again the balance, and the transfer happen. So how we preserve privacy? Yes, the user generates the proofs locally, as I said. The data is obscure because we use encryption and signatures. And of course, the user or the client is responsible to handling these nodes I was mentioning. So you have questions? I have, there was, yeah, I had a contact here, this one. Just in case you want to contact us. So if there are not questions, I think we will move on to the Google Meet. there is somebody from Starkware, right? He will connect and he will introduce you to how to prepare your computers to build all this kind of stuff. I will try to connect there. Let's see if this works. There we have Michael. Can you hear us? No.
Cool. Everyone,
Oh.
I'm actually from Exploration Team. Sorry, that is not as interactive as it should be because of the last minute replacement, but I'm trying to make it quick and insightful for you. So what we wanted to show you today is how relatively easy it is to build privacy-preserving applications with Noir using Starknet as a smart contract layer right now. And yeah, so we don't have like much time. So even installing like all the dependencies will take like a lot. So what I would suggest is to just take a look at the codes. So maybe like clone the repo locally and follow the steps. So there's like a guide, and you can. I will just like give you a quick walkthrough to explain what is what. So before we dive into the codes, so a couple of things. So when we talk about privacy preserving applications, so what we usually mean is two parts. So one part is what lives on the client side, and which is implemented typically as a ZK program or circuit. So in our case, we're going to use Noir for that. And the second part is like quote public part that lives on the public blockchain, and where we keep state, where we verify the proofs, and where like the business logic lives. Okay, so in our case, we won't have any state. So in this tutorial, so not even state commitments or nullifiers, and even encrypted state, no business logic, just a circuit, local prover, and proof verifier on Starknet, and that's it. All right. And what we wanted to achieve is roughly displayed on this diagram. So we have a Noir program, we have a smart contract on Starknet, we have lots of moving parts. So Garaga, which is a gluing thing, like a glue between Noir world and Carrier world, is everywhere. So it's used for code generation. It's used as an SDK on the client side. It's also used as a library in a smart contract. And if we put like all together, so we have an app. Essentially, we're like reinventing ad stack, but like using this combined stack. All right, so now I'm like switching to the code. So hopefully you have like already opened that. Let me know if you need a couple of seconds. Okay, so as I said before, right? So this workshop is pretty simple. I just combined the quick start from Noir and quick start from the Garaga toolchain. And if I put them together, so I can like build an app on Starknet, which preserves privacy. So, and we start with, so what we had to do is actually like install like all the dependencies. And if you have the codes, you can find like all the steps and like the commands you could run. Just like, so it's like a lot of different tool chains. So it will take a lot. So like assume that we already have all the environment installed. And the first thing is I have to have like a circuit, and I used the Nargo starter to generate a template project for me. So it's very simple. So it just does one simple thing. Okay, so
entry points, 2 inputs, 1 private, 1 public, 1 assertion. So this is like what you get when you like follow the Noir quick start. Okay, so we have this project generated, and it consists of the source file. We have also the Noir manifesto, where we have the description of the package, dependencies, and we also have like a separate file that is responsible for where we specify the inputs. Okay, so this is our baseline. Now we're going so this is like essentially the first part of the application I mentioned, right? So the part that lives on the client, so-called like private part. Okay, so we got our circuit. Now what we wanted to do is we want somehow to create a smart contract. Then we need to deploy it on Starknet. Then we need to generate like a proof and verify that on Starknet, and that will be essentially like the full cycle. And that's what I'm going to do right now. All right, very well. So first thing I'm going to do is, since I have my circuit, I can compile it down. So I have like regular like an alias for this command. So if we look inside, so it's just the invocation of the Narga, the Noir compiled toolchain. So what I have now is I have compiled the circuit down to the intermediate representation. Okay, and the next thing I need to do is I need to obtain the verifier key. Okay, that is like necessary to verify the proofs. And this is what I do using the ETHDenver toolchain. So, like in case you don't know, so Noir is one of the cool features of Noir that you can have like multiple proven backends. So the default and like most used backend developed by Aztec is called ETHDenver, and we're using exactly that with the special flower, the ultra hunk with tetra cache. So the ultra hunk is optimized for the proven speed. The downside is that the verification is much more expensive, but we'll like show that like on Starknet, so it's like still pretty cheap. We use like specifically to generate proofs really fast. So now I have the circuit compiled, I have my verification key. So this is enough for Garaga toolchain to automatically generate smart contract codes in Cairo, okay? And that's what we're going to do. So what we do is we call the Garaga, we say, okay, so we're going to use the ultra hung flavor. So this is the path to the verifier key, this is the name of the contract, and like voila, so we have like a bunch of files in Cairo. We have the what we have here is we have essentially like a smart contract written in Cairo that implements ultra hung proof verification. Okay, and this is like enough for us to just demonstrate the essence, right? So how we can settle like a Ziggy circuit on Starknet. So we have a smart contract. And it's like fully functional. So if we wanted to add some business logic, we could edit that, or we could compose several smart contracts to implement like a modular design. So what we're going to do right now is we're going to deploy that into Starknet. And like on Starknet, so it's done like in 2 stages. So first you need to declare contract. It's as if you are uploading the codes. And then you need to instantiate that. So first I do declare, and so luckily Garaga already has like a really nice command for that, so you don't need to use like any other tooling. what is happening like under the hood is the smart contract is being compiled, and yeah, so we obtain the class hash. It's like the hash of the compiled smart contract, and it's being submitted to the Starknet transaction. So it is done. Now I can deploy it. And this is like another type of transaction which relies on the class hash that we have declared previously. And what I said, now we have the smart contract that is living on Starknet testnet. It has one entry point that is called verify honk proof, and that means that we can already try to do that. So we have our circuit. We have inputs, both public and private specified, which means that we can generate witness, okay? And once we have a witness, we can produce a proof. Okay, cool. So that is like the only missing step is we need to somehow convert from the proof we obtained using the Noir toolchain to format that Starknet smart contract would understand. And that's here Garaga is like again acting as a glue. So what we do is we use Garaga to convert from the proof obtained to the smart contract arguments, essentially. So we specify that again, so we use the ultra honk flavor, so this is the proof, this is the verifying key, and we have produced the call data like in the raw format. And once we have that, we can finally, sorry for that, right, so we can finally invoke the contract. So we specify the contract address and the entry points, and here's like the call data we have generated from our proof. And yeah, so this is the result, the transaction that we have, that we got. And just to show you how much does it cost. So this is the transaction where we verify the honk proof. Cool. So this is all right. So this is the transaction. We had like submitted the proof and it was like successfully verified, and it cost us like a little less than 10 cents. So like it can be like further reduced to like 4 cents. So like a small tricks. Also like important thing here is we are like below certain limit of error steps. So without like diving into details, so that allows us to use proof verification in the transaction validation phase. So if you know about like account abstraction, so typically you have like two stages, like transaction validation and execution. And what it means is now you can have few-less transactions or some flexible paymaster, so you don't have to necessarily have a Starknet account or pay any fees. You can just submit transaction with the Noir proof, and it can like land on chain. Which is like pretty cool. And this is kind of like another reason why it's interesting to combine Noir and Starknet. So first, it's like it's super cheap. Second, you can do really crazy things with account abstraction. Okay, so last thing I wanted to share is the following. So, okay. We have settled Noir proof on Starknet. It's super cheap. It can be used with account abstraction to create some new experiences. What's next? So we wanted to do like even more cheaper. So how so the team working on Goraga is now looking into new flavor of the Gutenberg proven system. It's going to it will be called like Ultra Starknet Hunk, and it's in its essence we're like switching Ketchup to Poseidon, which is more ZK friendly, it's cheaper to verify in Cairo. And the Ultra Starknet Hunk certification is going to be even more cheaper. That's everything I wanted to share with you. Like again, like sorry for like that interactive format. If you have any question, please shoot. Here's the link to the Goraga. It's super cool. It's like it has really good docs, and yeah, I encourage you to take a look at it. Thank you.
Are questions for Michael? No questions, Michael.
Okay, perfect. Thank you. Have a lovely day.
Bye.
Bye.
He was here, right? So this is it. Thank you, guys.
Thanks, guys.